Good afternoon and welcome to the third webinar in the series BIM for GeoSciences. My name is Magnus Ramon and I'm working as BIM strategist here at NGI. Sorry, that was the starting page. Before we start with the presentation, I would like to have a short introduction to both GeoVita and NGI. GeoVita is a consultancy working with geotechnical engineering and rock mechanics within construction and transportation projects. GeoVita is located here in Oslo and have approximately 15 employees. NGI is a private research foundation with head offices in Oslo and offices in Trondheim, Perth, and Houston. NGI has approximately 320 employees and works with consultancy and research within the market areas geodata and technology, geotechnics and environment, natural hazards, and offshore energy. So today's agenda. First, Mona and Simon will have a presentation about environmental geotechnics. Here they will present how one can build a 3D model of contaminated soil based on site investigation, and how one can calculate the volumes the contractor must remove based on this model. Second, Nikolai and Mats will present how one can create and optimize the layout of ground improvement. They will also show how one can create an as-built model based on the installation data and how this can be compared to the design model. As in the earlier webinars, there will be possible to post questions in the chat. We'll try to answer some of them during the webinar, but in addition, all the questions will be answered and posted on the landing page where you all signed up for the webinar. The answer will probably be posted early next week. The recording from today's webinar will also be posted on NGI's YouTube channel during next week. So if you want to watch this again or share with some of your friends or colleagues, please visit our YouTube page. Here you can also find the videos from the two first webinars that we held earlier this summer and autumn. That was the practical information. Now over to the presentation and Mona, who will start.
Yes, my name is Mona Hansen, and I work as an environmental engineer here at NGI. One of the topics we are working on is contaminated soil, both with the remediation project, but also on construction work on contaminated areas. We work towards good solution regarding both to the exposure of the contamination to human and nature, but also on the best logistics and economic solutions. And to help us with that, we have the last year worked on a method to do 3D modeling of contaminated soil. I will kick off this presentation with the background for the work and how we collect the input data to the model, and show you how we present the data until today in 2D maps. And then my colleague Simon will present an example of a 3D model from a project in Norway. So a bit about the ongoing trend and why we wanted to go to 3D modeling and BIM. Especially with infrastructure projects, we see that the projects are large and complex. There are often several phases for preparatory works before the main contractor, which often gives different volumes of contaminated soil in different phases of the project. There are increased requirements to deliver digitally into BIM platforms, and we see a general transition from drawing to a model-based workflow in the project. And to get the environmental part of this project in early into BIM, we can enable to do more collaborations. And this also brings me to the last point. Today, there are increased requirements also to sustainable geosolutions in the projects. And today the surplus masses often are classified as waste. So this 3D modeling can help us maybe see solutions for that. So a bit about input data in the environmental project. The environmental engineers are often interested in the topsoil with sand and gravel, often fill material, down to the naturally deposit clay, as we see in this picture. This is normally at a few meter depth, as also the picture shows. The ground investigation will include drilling rig or an excavator to sample the fill material in different layers. We log the lithology and sample the fill material and send it to the chemical analysis in a lab. Here we detect the contamination levels and we classify the soil within the Norwegian classification system from class 1 to 5 with the increasing contamination levels. And this gives us a typical Excel sheet that you see here with various classes in points and depths. From the classified soil data, we are today drawing maps with different contamination levels as a 2D map. We have to make different maps for deeper layers, as you see on the 2 examples there. This is a park in Oslo, and there is no lithology in these maps. So we are now in the transition from drawing over to a 3D modeling. And in this work, we have used the program LeapfrogWorks. This creates a dynamic 3D geological modeling, and it's designed for civil engineers and environmental projects. We do a numeric modeling with the chemical data in the boreholes, and LeapfrogWorks uses the radial basis function, RBF interpolation, with a mathematical algorithm. So this interpolates between the data. So with this said, I think it's time for Simon to present an example.
Thank you, Mona. Yeah, so I'm now going to do a demonstration of the workflow we're currently using to create 3D models of contaminated soil using LeapfrogWorks. In the BIM for GeoSciences webinar 1, my colleague Per-Anders Mortensen did a presentation about LeapfrogWorks and how to create models of soil layering. So in this presentation today, I'm going to focus on how to use the soil layer model to create a 3D model of the contaminant distribution. The way we do this is by using the soil model as a spatial boundary for the contaminants. To demonstrate this, I'm going to use a case study from an ongoing project we have here in Trondheim. It's an infrastructure project by the Norwegian Public Roads Administration, where we are planning to build a bicycle path and walkway between 2 neighborhoods in Trondheim, Norway. Despite its rather small size, the project includes multiple disciplines, including engineers, architects, city planners, and so on. The area where the bicycle path and walkway will pass through is the former ferrosilicon smelter that was active from 1927 to 2002. So if we look here at the area, we have the green line mine, and in the upper right part of the aerial photo, you can see the ferrosilicon smelter. In this central part of the area, we can see how there's been stored waste from the smelter process. But there's also these 2 areas here where it's quite evident that there's been stored coke or the fuel for the smelter process. So we expect to find remnants of these contaminants there, which will most likely show itself as elevated concentrations of heavy metals or polyaromatic hydrocarbons. So just a quick agenda for the presentation here. I'm going to show how to use the topography and import buildings into your model, importing the boreholes and the lithology from the boreholes, and then using those to create the geological model of the area. You can then start to look at the contaminant concentrations from the borehole samples, and finally use these to create a 3D model of the contaminant distribution within the soil layers. Afterward, I'm going to focus on how to edit your model and how LeapfrogWorks can be used to interact with other disciplines and calculate excavation volumes. A bit about the workflow. The starting point is two Excel spreadsheets where you collect your the geographical coordinates of your boreholes and the depth of your boreholes in one spreadsheet, and the lithological and chemical data in another one. In addition, you need a good topography model and a model boundary, and this can be imported from CAD software, but it can also be drawn inside LeapFrogWorks. So here you see I've imported the topography model and the boreholes with showing the lithology within each borehole. The yellow layer is sand and gravel, where we find the fill material and the contaminants, and then the blue, light blue layer is the clay underneath. Here I've imported the project outline from drawn in a CAD software, and I can then use this to define the lateral extent of my geological model. Then we can start to look at the contaminants within the boreholes and the specific intervals. You see here the samples have been classified according to the Norwegian classification scheme, where purple includes the dangerous waste and red is the most contaminated soil. So here you can also look at specific parameters. Here I'm looking at lead, which is and when also compared to other parameters, here it's the polyaromatic hydrocarbons. In total, you can use these to these borehole data to interpolate between the boreholes and create a 3D model of your contaminant distribution. The way LeapFrogWorks does this is by using an RBF interpolant, as Mona talked about earlier. It lends from some geostatistical concepts like variograms and sill, drift, nugget, and so on. And you can manipulate these parameters to make the model fit your field observations better and make a trustworthy model of the contaminant distribution. If you know from your field observations that there is a general trend in your data, you can also apply this to your model using either structural data or by defining a plane with a dip and an orientation. Finally, you can edit your model by doing manual edits. In this case, we have a class 5 sample in the top of this borehole that shows up as a quite small volume in my model, and I want to edit that. So I draw a polyline, the green line you see in the middle of the screen, and then the model automatically updates itself according to that and fits all the observations, including the boreholes, to these adjustments. And then you can afterwards inspect it alongside all your other data and update your model gradually. LeapFrogWorks is also very suitable for interacting with other disciplines. Here I've imported a CAD drawing of a kulvad and you can then use this visualization of the interaction between the different disciplines to see like where the construction cuts the topography, or which soil layers the construction will be placed into. The same thing can be done for water and drainage systems and sewage systems, and make a good visualization of this. And if you do, you can use this as a tool to interact with other disciplines as well. So, for instance, in this case, we wanted to place the sewage system so it didn't cross through the most contaminated area. So we avoided having to handle so much contaminated soil to build this bicycle path. Finally, here's just a screenshot of a view of how it looks when you open up the program. This is from another project here in Trondheim, where we have detected a contaminant plume of containing high concentrations of lead, primarily, that crosses through an area where we need to dig a ditch to place high voltage cables through the area. So one of the features of Leapfrog Works is you can do slices of your model, where you can gradually look through your model and see how it looks in a plane. So here you see how the contaminant is actually a very thin layer contained in the top meters of the soil in the area in the area. You can then import 3D models of the ditch geometry and view that in Leapfrog Works. You then merge it with the topography, so make the ditch cut into the topography to view the topography of the area after the ditch have been dug out, and then you can use your contaminant model to see how much of the contaminants are contained within the ditch. And an advantage of using Leapfrog Works is that the excavation volumes within the different contaminant classes are automatically calculated. So here you see, for instance, that in class 2 we have about 225 cubic meters of that, and that would be very helpful information for the constructor to plan for how to handle the contaminated soil. To say, and back to you, Mona.
Yes, to summarize the work you've seen today, we have made a geological model based on the lithology observations, used that into a numeric model based on chemical data from borehole samples. With this work, we believe that we have increased the value from each data by the interpolation work. We also believe that we can have a faster workflow with the automatic computation of the excavation volumes. And this also gives a more transparent workflow because we model instead of drawing, and the evaluation that we makes the edits in the model are traceable in the program. So this is the end of this presentation. Hope you found it interesting. And we will continue with the presentation from Mats and Nikolai.
Hello, everyone. This part will be jointly presented by me, Mats Karlström from NGI, and Nikolai Börner Hansen from GeoVita. We will showcase how the principles of parametric design in Rhino and Grasshopper may be applied to construct ground improvement models for both the design phase and the as-built deliverable. Let's start by looking at what ground improvement actually is before diving into the scripts. So there are several methods to improve the strength and stiffness of the ground. We can use vibration, impact, or by mixing a binder material into the soil. In this presentation, we will focus on deep soil mixing, known in Norway as lime cement columns or kalkcementpeler. With this method, a dry binder, typically lime and cement, is mixed into the soil using air pressure and a rotational tool. These columns can be approximately 20 to 30 meters long and have a diameter of approximately 600 to 800 millimeters. The columns are installed in various patterns, such as grids, ribs, panels, or single columns, depending on the purpose and structural function of the ground improvement. And to the image in the right side, you can see a typical panel grid type pattern. This method has been used in Sweden and Japan for many years, and also in Norway. Large construction projects in soft clay areas may have several tens of thousands of these columns installed to improve the constructability and reduce the ground risk. For example, when constructing a deep excavation in soft or highly sensitive clay, ground improvement columns may be installed in between the retaining wall system to provide lateral support, as shown in these illustrations. So, why do we believe parametric design is suitable for this? Well, this is because ground improvement 3D models often consist of thousands of individual objects arranged spatially in repetitive layouts and patterns. In addition, a modern design process is highly iterative, and our proposed design is likely to evolve significantly as our model maturity is increased. Therefore, I would argue that ground improvement is tailor-made for parametric design. So let's check out when Nikolai demonstrates this.
Thank you, Mats. For those of you who watched part 1 of the webinar, I've already introduced myself there. So if you did not see part 1, please watch it. Not only to see my introduction, but first and foremost, we go into a little more detail about how we use parametric design in our workflow on a general basis. That said, we jump straight into Rhino. I have already imported my existing terrain, shown in green, as well as bedrock, shown in gray. Into Rhino, I have also predefined our outer area, where we want to do ground improvement, shown with this red polygon. We have also an existing building as a kind of a area where we want to sorry, we also have an existing building as a kind of area where we do not want to do ground improvement at all. Furthermore, we have an excavation level for a new water pipe, as well as the water pipe line itself. And the water pipe line is, of course, the one with red. And the reason for these different object types is that they are a good example to let you see how we, simple and dynamic, can have different types of deep soil mixing patterns, like Mats explained, merged together, as well as differentiating between the strength in one single column. So switching to Grasshopper, I've already prepared my script. That is imported the transformation part, and I've already taken in the attribute part, and so we'll just start with applying our deep soil mixing component. Setting our in data in Grasshopper, as we used to. Again, the terrain, the bedrock, and this purple excavation surface. And the excavation surface acts as a way to divide the columns into different variations. Because, for example, we do not want to dig into full strength columns when the water pipeline is to be established. So, and then making a grid of piles or columns, lime cement columns, choosing our outer area, and we'll define either a triangular or a square pattern, just to switch here in a Grasshopper. So when done, we're just setting the right rotation, so the grid are roughly perpendicular to our outer boundary. So we'll just do a bit adjusting on that. Let's have a look. Okay, make it 26 here instead, and then we're good to go. We like that pattern. So as well as we can adjust a bit on the center distance of the grid in both X and Y direction. And so let's set that to 4 meters here. And we can just as well finally choose the desired or the calculated dimension of the lime cement columns. Okay, but what about the building? Then we just choose, like we used to, our exclusion area in the script. And voila. Okay, might take some seconds here, and this is by the way in real time. So now all the columns in that area are removed. And what I don't show you here is that you easily could adjust the exclusion area as well as our outer area in Rhino, and the pattern will automatically change. So let's have a look at another type of pattern. In this example, we used the water pipeline, but this could just as well be a railway or a road alignment. And this type of pattern with double or even triple panels is, like Mats mentioned, widely used in Norway. Like the grid pattern, we have the option to do different adjustments, such as length of the panels, overlap between panels, center distance, angles, etc., etc. Moving down to these fields, in which I type in some Norwegian text, this applies to our model attributes, which I will come back to later in this session. So just finish up those. And then, so I think let's have a look at our model when we deactivate our sketch mode. I think here we have options for that, so we don't get all the 3D in at once. So we just deactivate the sketch mode and activate the 3D Rhino view. And then of course it has a bit of working to do, but like you see here, we soon have the 3D lines in Rhino for both the grid and the double rows. And you can set the reason for these options are, like I said, due to the fact that working with pretty large models could and often will result in high CPU usage as well as memory usage. Here we have all the lines, and we got those different colors for the different patterns. And we could just take on the full 3D view, like the columns. We'll see here as well. All the columns down to our bedrock and different color for the panels. As well as we don't mix the different patterns, so they are merged together and excluding some of the green ones where we have the panels. Okay, so if we have a look in Tekla structures, like we showed you in the first part, there's a live link to Tekla structures where we do all our models at the end, just to make the IFC out. So it's looking good from all sides and all angles here. So moving on, I would like to talk more about attributes. I talked a bit about it in the first webinar, but at a very superficial level. So there are of course many ways to do this, and I will show one of the ways. But please have in mind that this is the way best suited for our needs and how we do it at our company and in our projects. And that may not be the best way for you though. Okay, early on, right beforehand, when modeling the deep soil mixing, I entered the Norwegian text in an attribute field, which I made a screen print of here. And sorry, The reason for this is that this component in Grasshopper and the text are linked up to an Excel spreadsheet, which contains all of our attributes. And you might say this could also be a database. If you have tons of attributes, that would be perhaps a better solution. And this connection is, of course, also programmed in Grasshopper. So just have a closer look at the spreadsheet. We have different sheets for different kind of models. So we have one spreadsheet for all our attributes. And let's have a look at the sheet named ground improvement or grundforstärkning down here. This is where all information regarding the deep soil mixing are. Is it a wet or dry mixing? What quality do you need? The ratio of the mixing, the rotational speed when injecting, and so on, as well as the object code, which is linked up to the Norwegian documentation. As well as a ground protection sheet name, we also have a sheet name that handles the attributes regarding general information of the model, such as model name, project name, coordinate systems, model maturity index, and so on and so on. And what we think is good about this system is that everything is gathered in one single spreadsheet, and it can easily be adapted to the requirements that may be in each individual project. So we make this project-based. But let's have a look at the actual IFC model exported from Tekla, just to see if those attributes actually exist. And in this example, I've used Trimble Connect, and I also talked a bit about Trimble Connect and the big advantages of collaboration in our first webinar. So again, if you have not seen that yet, have a look at part 1 webinar. And if we have a closer look, we'll find the same attributes as we saw in the spreadsheet earlier. And those attributes regarding deep soil mixing, such as pile ID, pile number, amount of lime cement, yeah, all those we looked at in the spreadsheet. It's here. And you see if we click on the different type of columns over the excavation area, and on there we have a different amount of cement due to the fact we have to dig those away. And like you see here, we have the same model info as well. So everything is linked up from the Excel spreadsheet. We get as well as some base quantities, a length and a volume of the individual columns. As you can see, it's running quite smoothly in the browser version of Trimble Connect as well, despite being a quite big model with around 17,000 objects, around 9,000 columns. But as Matt mentioned, some projects have up to 50 or 100,000 columns, so it can be quite big models. And just doing a quick check with the backtrack model to see that everything looks fine, as well as the existing terrain. Just loading that one. And you see here we could do some vertical clip planes as well. And you get a good feeling about how it looks like. Okay, jumping on, I would like to do a quick quantity takeout from the model as well, and just not some base quantities of a single base quantity per object. So if we select our entire model and head down to the data table icon or menu, we get, yeah, just after a couple of seconds loading time, and this is also in real time, we get a table showing all of our attributes, as well as the length and the volume. And the good thing about this is you get it both individually and summarized. And you can first we see it by all its individual objects, but then I just drag this object name up here, and I choose how to group this. And then you can see we get the length and the volumes, etc. summed up. And you could, of course, group it according to your own terms. if you have special needs. But I took a little bit further. Like you saw here, I did an export of this table to a CSV file. And I'll just open up this file. And like you see here, it's not very fun to look at or to work with. So just in good grasshopper spirit, I made a quick script which reads the CSV file. And then the script sums up, like in Trimmer Connect, the total amount of cement used in the model, but also you can hook up the price of the cement and even the amounts of CO2 that would be emitted by producing this quantity of cement for this actual case. So, and here you have a lot of opportunities like this one where I just could change the original 75 kilos per cubic meters of cement just to do a scenario where I reduce this to 70, and I could see what is the price difference and the quantity difference, as well as the CO2 difference in using a little less cement. So kind of cool. So just a quick sum up of our model. What are we handing over to the contractor? First, a highly detailed IFC model with project customized attributes. And these attributes will of course be developed in collaboration with the contractor. We deliver a model fully optimized for easy quantity takeout and performing price estimates. That said, we are in the process of looking at how to get the model fully 4D and 5D BIM ready. The 4D adds an extra dimension of information to the model in the form of scheduling data, and being able to extract accurate costs information is what is actually the heart of 5D BIM. And I would say that we're pretty close at 5D BIM here. We are currently adapting this to all our scripts, and I think that this will actually open up a whole new world for planning at an early stage. As the final bullet point say, a design model with model maturity index 400 that can be used to compare the design and as built model. And this is actually an essential point for us as a consultant. Where were the differences? Why was there a difference? And what can we learn from it for the next project? So to talk more about as-built models, I'll pass the baton on to Mats. So thank you for listening, everybody, and back to you, Mats.
Thank you, Nikolai. So now we are at the end of the project, or at the design phase. Installation work is underway, or it might already be complete. And the client is requesting the as-built model of my ground improvement. So how should I proceed and do this? One simple solution could be to take the MMI 400 ready for construction model, change it to MMI 500. I give the model a new date and I reissue it to client. But that would possibly not be entirely correct. As Nikolai mentioned, during the installation works, it is highly likely that things have changed compared to the model I had in my design. So instead, maybe we can use and combine the data from the installation process with our data from the design process and reconstruct a new 3D model, and also compare this new model against the design model. So this is a flowchart detailing how we have chosen to manage this data process, how to build and take as-built data from the ground improvement, from the production, and create the finished IFC model based on the as-built data. So first we take the ready for construction model and break it down into a data table and merge it in Python with the as-built production log that we receive from the subcontractor. Here it is important that you, at the start of the project, create a unique key for each column, preferably the column ID, because this is what you can use to merge the design and the as-built data tables. Next, we need to clean the data and check for errors in the production logs. Sometimes we need a few iterations with the subcontractor in order to obtain a complete data set, because when installation is real time and things go quickly, it is often that you miss some small details. The cleaned and merged data can easily be imported to Grasshopper, where we generate 3D objects based on these data tables. And as long as we for each column specify X, Y, Z coordinates and some other geometry information such as length and diameter, we can rebuild the 3D objects for each column. Next, we need to analyze the model and check if the installation works are acceptable. If not, we may need to propose some remedial measures, such as installing additional columns. And if there were no issues, I think you've earned yourself a break and a nice cup of coffee. Finally, once the as-built model is complete and there are no more errors, we can append the metadata as shown by Nikolai and issue the model in IFC or any other preferred format to the client. So now I'm going to show two things. First, how we can construct the 3D as-built objects in Grasshopper based on tabulated data from the installation works. And secondly, how we can filter and query and visualize these objects based on some metric such as a deviation using control curves. And this forms a good blend between a semi-automated workflow and hands-on interaction by the engineer. And the data in this demo is from the Intercity Drammen project, where Veidekke is main contractor and Bane NOR is client. And as similarly to Nikolai's presentation, to the right you can see my Grasshopper script, and to the left is the Rhino viewport. So let's start. But before we dive into the script, we can review the data table that I will use as input. This file is already pre-processed and it contains as-built data from the subcontractor, approximately 3,800 columns that were installed this summer. Prior to loading, the data has already been cleaned and merged in Python, and in my opinion, this is more convenient to do outside of Grasshopper. So it contains all the information I need to rebuild the model in 3D, and it also contains the length deviation between the design pile and the as-built pile as calculated in Python. So let's go ahead and load this file into Grasshopper. And it takes a few moments for it to process the data. In Rhino, I've already preloaded some terrain contours and the moraine boundary surface to which we will install the columns. Okay, and now we can view the as-built 3D model of my columns. All columns have been processed and turned into 3D objects. And basically, I could just append metadata now and issue this model as an MMI 500 as-built model to the client. But I want to do some checking. So I'm going to turn on the sheet pile wall layer and check to see how the columns are interfacing with the sheet pile steel plates to see if we have a good load transfer. And it looks pretty good here. Another thing I want to do is to compare my as-built model with the design model. So I'm going to go and turn off some of the layers I'm not going to use now. And then this script basically checks the length deviation that I calculated during the pre-processing and groups the columns in various categories depending on the length deviation. So basically, I want to find out if some of the columns that we installed were too short. I've set the length criterion here of 0.5 meter. So if the columns are less than 0.5 meter too short, I'm not going to bother with them. I'm going to run this through a filter function, and then I can visualize and group the short columns based on a red, green, and yellow color scheme. So as you can see, I've now turned off the as-built model, and now only the short columns are shown. In order to help this visualization a bit, I'm going to create a legend in Rhino, and I need to assign an anchor point. So I'm connecting the point to Grasshopper and creating a legend. This is quite convenient for taking some screenshots and using the reporting. And as you can see, the short columns are rather clustered in 3 or 4 groups. So I want to analyze these a bit more in detail to get some statistics out of the columns. So I'm creating some boundary curves here to circumference the columns I want to analyze closer. And I will connect these curves to my Grasshopper script. And then my Grasshopper script uses these curves to filter out and basically cluster the columns into 3 groups. So I'm running it through the group column function and then pushing the data into a function that basically computes some summary statistics. So we can see that in my 3 groups here, I have 477 columns, and I can, in this panel, list all the deviations for each column. I can also review some group summaries. So I have 3 groups, and I can see the column count. And all columns are minimum ½ meter too short, as set by my criterion. The average length is about ½ meter to 1 meter too short, and the shortest column is 4.5 meters too short in the first group. The reason for the columns being short is, in this case, the moraine surface being slightly higher than what we predicted during the design phase. So this will not pose any issue for further construction, but it's good to be aware of this when you move on. There can be other issues that might not be acceptable. So finishing off, some key takeaways here is that as-built data, when you do groundwork, often deviates from the design. And by using Rhino and Grasshopper, we can easily visualize and analyze the as-built data that comes in tabulated formats in 3D. And the evaluation of the as-built data is very important in order to reduce the ground risk. Thank you.
That was all for today. We hope you all enjoyed the presentations. And if you have any questions or want to contact any of us, you can find the email addresses to the presenters here on the page. We are planning with a new webinar in either December or January. More information will come in social media, both about the time and the content. So please follow GeoVita and NGI on Facebook and LinkedIn for more information. I would like to thank you all for joining the webinar today, and I wish you all a nice Friday evening. Goodbye.